Oh, you're on mute. So next to the little screen, there's a little microphone button to switch on.
Is it okay now?
That's perfect. Thank you very much.
Okay.
Thanks.
Yeah, thank you for the opportunities to speak and for the kind introduction. I'm also one of those who has very fond memories of the Bristol workshop on cryo and CLEM. So this is another CLEM talk here. We will focus more on the optical side rather than the EM part. And this work is a collaboration between Aurox, NPL, and Linkam. So we will talk about a practical topic, how to integrate the cryo system in your existing setups and how to make the workflow more smooth. So first, we will start talking about the benefits of cryo for those who are probably not yet on board with the technique. The different independent motivations why you might do cryo and correlation, focus on some workflow options, and then we'll home in onto the problem we have solved for extending the platform to inverteds, and then show in more detail the adaptation optics we have built for integration, for the physical integration, as well as some software work. So here are the main reasons for cryo. So the EM gives you all the very high resolution and also the structural context in the cell, but the labeling techniques are not yet as versatile to flexibly highlight the things you might want. And so fluorescence is still very useful and very specific labeling technique, and it has low resolution, but it can still help you to find regions of interest. The cryo preparation, cryo preservation helps you to keep the cells in your biological sample in a near native state, because it's fully hydrated and is still compatible with the EM that with the vacuum that the EM requires. Throughout the workflow, you will need to keep your sample colder than -140 degrees Celsius, because otherwise you will get crystal formation and that will destroy the ultrastructure of your sample. That's an image from the Dubochet paper that most of you have probably seen. There are several branches of the cryo and correlation particle EM technique where you don't use the imaging capabilities of the optical techniques, but for the particle EM, which got a Nobel Prize not too long ago, you can use the cryoimaging to inspect the quality of your sample preparation, which is quite crucial. You normally have particles that are all the same, so you only in some experiments you might need to identify different types of particles, but still the optical imaging is very useful here, because you can monitor your sample quality, and therefore you would not take samples to the EM and use up valuable EM time when you can do this pre-screening step. There's a completely independent motivation for doing cryofluorescence, and that is the photobleaching. So in cryo, dependent on the type of fluorophore you're using, you have much higher signal and also reduced photobleaching. So in total, you get many more photons out of your sample before bleaching happens. And all the mechanisms are not yet understood, but it's assumed that the diffusion of oxygen plays a major role in the bleaching events. And because you limit diffusion when you have a cryo embedding, you are also reducing the bleaching events dramatically. And this bleaching has another implication. This borders onto the methods of fluorescence superresolution. In the superresolution techniques, not sure if you can see my cursor. Yeah, in the superresolution techniques, what you're doing, at least in the single molecule techniques, you're localizing individual fluorophores, and the localization precision is influenced by the number n of photons you have available for this process. And as you expect, if you go to cryo, if you have in some cases 100 times more photons, you can in principle improve your localization precision by a factor of 10 in this case. There are many workflow options. Usually you would start with in vivo fluorescence imaging. You would then, to produce a cryo sample, use either plunge freezing or high pressure freezing. The choice of those techniques will also depend on the thickness of your sample. High pressure freezing can extend to larger cells. Plunge freezing is typically used for single cell layers or single cells or particles. And you would then normally follow with cryo-Fluorescence to inspect the sample after imaging, and also to map your sample and to be able to locate it easily and quickly. The other independent benefit of cryo-correlation is also that if you have a navigation map of your sample, you can take it to the M and you can go directly to that region of interest, and you will not waste beam damage. So you will get your optimum sample image data and optimum signal to noise immediately, because you don't need to use EM and beam damage for localizing your sample. Other techniques you can use to connect is, of course, cryotomography, X-ray tomography, or normal X-ray, or zero block phase scanning, or all these techniques available. In the next part of the talk, so before I've discussed why cryoimaging and cryofluorescence, optical cryoimaging is useful, and now we will look at the physical practical integration, and also show what problem we have solved with our design. So in general, most biological labs will have a dominant variety of inverted microscope systems. However, the standard or most common stages, in this case it's the Linkam stage, of course, I'm talking about, is designed for an upright system. There are reasons for that. It's a special chamber design where the chamber is self-cleaning. It's creating a constant flow of clean nitrogen gas out of the sample chamber, and therefore avoiding contamination. So this was initially designed, this design was initially done for an upright system. However, most labs, most biolabs have most commonly inverted systems, and it would be nice to make the technique more widely available by integrating standard cryo stages to inverted systems. This shows a standard upright system and illustrates the workflow so far. This has been tried and tested. It's possible to work like that, but there are still a few steps you need to do to load your sample. On the right-hand side, you can see here where the stage is taken off the microscope, and you get full access to the sample chamber to load and manipulate your sample. But it is a few steps, and as mentioned before, it's that inverted microscope which you may not have as a biolab. Yeah, so it's several aspects. So it's the mounting, the unmounting, and the remounting of the stage, being careful with cables, with nitrogen supply. So there are a few things to watch out here. To solve this and to be able to still run and operate a cryo-optical system on an inverted design, we have designed an inverter scope system, CryoInverter, which mounts onto an inverted design. It is a 4F optical system, and it is let's look at it. So the idea is you tilt things out of the way for simple access, and you will need to image the pupil plane of the original microscope host system to match the new mounting position of the lens. Here you see on the left the cryo stage as is mounted on the inverted, and here's a detailed view of the sample manipulation, the sample holders, the magnetic cassette, and also the sample bridge and the cryo transfer boxes. Because the objective lens dips into the cryo stage and the travel range is quite limited normally on inverted systems, usually maybe about 10 millimeters, it is not possible to just move the focus out of the way and then slide the stage forward. So therefore we ended up with a special tilting system that gives you full access and also doesn't require to move the focusing position of the system. Here you see the layout. On the left, so there's a breadboard integrated onto the standard inverted frame. Then there is a dovetail mount that accepts our stage. That would be the same layout that you will have normally on an upright system. And here you see the whole thing mounted together with sample access. Here without the stage, you can see the tilt arm and also the part that attaches to the nose piece. And you have here on the right, you see the full overview. You see of course, the Aurox clarity, the confocal attachment, the LED illumination part here, camera, and the rest of the system. So this design has been integrated into the Aurox software world, so into the visionary system. So therefore you can also do grid mapping and Z mapping. Z mapping is based on the focus drive on the microscope, and the XY is controlled is physically done by the cryo stage, but it's controlled by the visionary software. After we built this, we of course wanted to know whether the optical performance is compromised, and we wanted to measure and verify. So to do that, we have done 2 experiments or 2 comparison runs. We have checked with beads on one comparison setup where we mounted the lens directly on the nose piece, where we would have mounted directly here and scanned the beads with the immediately mounted design, and of course the other one where the cryo-inverter setup is in place. And to do that, we have done statistics on beads. We used a very useful tool which is called Metrology, where you can automatically analyze a 3D volume which contains the bead, and it will produce all the metrics. And we compared those two, and here's the statistics, the result. So it had a slight effect on the PSF in Z, the Z extent. About 18%. We can probably still improve on that, but in general, the PSF in Z and in confocal and structural illumination systems, in a paper which analyzed these conditions and how stable they are, they quoted, it's the Cole paper, which in Nature Protocols, which said there may be a variance of, they found 11% day to day. And our numbers compare very well. This is the spinning disk system from Aurox, the Clarity, but it compares very well with also the data shown in the Cole paper for point scanner. So that was a very encouraging result. Here we have some cryo images from HeLa cells. The top one is zoomed out with a 10x. It's just an overview. In the lower region, you can see still the support film, the quantifoil, and some details of the HeLa cell. So this was recorded with 100 times 0.9, and it's a maximum intensity projection of the stack. And here we see also cryo data done with a Clarity system. On the left, you see wide field, while on the right, you see the confocal. And yeah, it's a fly through to the stack. It's an example to show the integration. Okay, I hope that was playing okay. Oops. Yes, and we have already arrived at the conclusion. So with the tilt system, it is possible to integrate the standard Linkam stage that is now very widespread in the world into also an inverted platform. It gives improved convenience for the sample loading. There is potentially, if you only have inverted microscopes, or you would need to buy a new upright, then of course there's a cost saving. And so far we found that the effect on the PSF is noticeable but acceptable. And we have also demonstrated the whole integration into the Aurox system and the Visionary software. And also there is now a micromanager driver for integrating the Linkam cryo stage into the micromanager world or ImageJ world. So if you want to go down that route, there's also now an easier path. And yeah, that is the summary so far. Thank you for listening, and I'm happy to take questions.
Thank you so much, Michael. That's a really good talk, and I've really enjoyed working with you and Stephanie and Kirti on this project. So we've been working with the National Physics Laboratory as part of their Measurement for Recovery program. If you're from a company and you're on this meeting, I do encourage you to contact National Physics Laboratory. I know Stephanie's online here at the moment. I think Kirti might be as well. It's really been a brilliant opportunity to get some research projects and things done while we haven't had time to go out and see customers and things like that. So it's been great fun working with you, Michael, on this. I'm happy to open this up for questions. So there's a couple of questions from Paul Vicada. So he says, great development. 2 questions. Is this already commercially available? And what about condensation on the objective when tilting the lens? So 2 quite different questions for you, Michael.
So first of all, at the moment it's a prototype, but if we hear more questions like that, we are planning to commercialize it. So yes, it will be commercial. So the objective lens, if you tilt it out, yes, the tip may have condensation, and you may need to dry the lens in some cases. It depends for how long you tilt it out. So yes, that's a valid point, but it's not a practical sort of roadblock. So good point, but yeah.
I guess that problem would happen if you were on an upright system and you had to remove the stage to mount the sample anyway. You'd still have to make sure your lens was dry and free from condensation before you put the stage back onto the microscope. So it's probably a universal problem, I guess.
Yes. Also, it depends on. I mean, the lens is mounted onto more metal parts, and the heat transfer to the tip of the lens is not that high, and because it's quite a large metal mass, it takes a long time to cool down. It's relatively steady because of the mass. So you may not see this problem all the time, but if you get condensation when you retract it, then it's also no problem to dry it.
Sure. Any more questions coming up in the chat folder? Not for the moment. Paul says thank you. Yeah, so I'd just like to make one point that obviously this implementation on the inverted microscope is very, very new, but also the software integration that we've done of this Linkam motorized stage into the Micromanager and Visionary software will also work on an upright microscope. So this is very much to assist people if they already have a microscope that they want to use for cryofluorescence or cryoconfocal, then they can now upgrade this system in a modular way. So they can add the cryo stage and or our confocal without a huge commercial outlay for one of the more integrated platforms. So it's a really, really exciting project that we hope to carry on and finish off and make it commercially available to everybody. But if anyone wants information, then either contact Michael or you can contact myself as well. So have you got anything more to add, Michael?
Just to thank Kirti Prakash, Stephanie Ray, and Mike Shaw at NPL.
Yes.
You did already mention those, but I should have said it more
yeah, they've been really
boldly in the beginning. So yes, thank you so much for this collaboration.
Yeah.